Hi everyone, Professor Robert J. McEwen here. Welcome to my video on calculus with advanced functions. We're going to cover the second half of chapter 6 in our textbook. What can you look forward to today? Well, first, what did we do on the last video? We introduced calculus. We introduced calculus with limits, gave you some intuition on what calculus is, what we use it for. We talked about tangent lines. We talked about the slope of those tangent lines was really the geometric interpretation of calculus, right? What we're trying to do. We want to find the slope on the point of a kind of curving function, not just a straight line, but something more curved. And so today we are going to cover the most important topic in this entire course. If you remember just one thing from this course, I hope it will be the second half of chapter 6. Because if you think about what we did in the last video, it was a lot of work. It was a lot of work to find the derivative of a function. We had to use that Newton quotient. We had to take the limit. It turns out that there are a whole bunch of derivative rules that can make our lives easier and allow us to take the derivative of more advanced functions quickly. And as an economist who's using calculus in economics, this is really what you want to be able to do, and this is what your professors in second year, third year, and fourth year are going to expect you to be able to do. So this is the most important topic of this whole class. Chapter 7 builds on what we do in chapter 6, so if you don't get chapter 6, chapter 7 is not going to make any sense to you at all. Same with chapter 8. Chapter 8 relies on chapter 6. It's maximizing, optimizing. It's not going to make any sense unless you nail the second half of chapter 6. And then chapter 9, integration is very useful, but that's a different type of calculus that we also use as economists, but maybe not quite as frequently as we do the derivative calculus that we're going to be talking about today. So that said, I hope you have a pen, you got your paper, you're focused, and you're ready to work. We're going to go through a whole bunch of different rules that you're going to be expected to know, a whole bunch of different examples, and I hope you enjoy the videos, and let's get to it. Here's our outline for the topics that we're going to cover, all the different rules. I'll let you look over this yourself. Think of it as kind of a study guide after you've watched the videos and done some practice problems. And then in the very last video part for this series, I'll go through each of these and do a review of all the rules we've learned. You can see there's a lot of them, and so you've got your work cut out for you in terms of learning, i.e. memorizing these rules. These are rules that you memorize. There might be some intuition to them, but for the most part, you're going to memorize them, and then you're going to apply those rules to specific problems. And we're going to do that in the video. You're going to do that when we have our weekly Zoom sessions, and you're going to do that on term test 2 in the final exam. As I said in the introductory video, this is the most important topic in this course. This is what you need to know going forward. And if you forget a rule a year from now and it comes up in one of your microeconomic courses or your labor course or what have you, you have to be able to go back and remind yourself of what that rule is. And the best way, of course, is just to know the rule and not forget it. Now we saw that there were the limit rules, and we saw that in the previous videos. And if we let that limit go to a point so that h got very close to 0, and the function was differentiable at that point, we could find the derivative. And this process is called differentiation. Differentiation, right? This is derivative calculus. We're learning derivative calculus. And also, as I said in the introduction, it's much more common to use rules rather than the limit method that you learned in the previous series of videos. Now, going forward, every time I introduce a rule to you, I don't want to have to tell you that I'm assuming the function is differentiable on some interval between a and b. We're going to assume that all of our functions are differentiable. I don't want to give you the definition of differentiability. That's a little bit abstract, but we're going to assume that a derivative exists for all of the functions in all the videos in this series of calculus with advanced functions. So we can assume that all functions are differentiable, right? This suggests that sometimes functions are not differentiable, or they're not differentiable at a certain point, but you don't have to worry about that, not in this section. Now, when you were doing your homework for calculus, the introduction to calculus, you might have noted that constant terms disappear, right? So if we look here at this function, we see that we've got a term that's a function of x. I could rewrite this as f of x is equal to g of x plus some constant. I could call it a. So that's a very formal way of writing out this specific example, but we know that if we take the derivative of f of x with respect to x, we're going to get the derivative of x with respect to g plus 0, plus nothing. That a is just going to disappear. And the intuition behind that is really quite simple. So I've drawn a diagram here, and I'll just create some curve that looks like that. And we'll call this g of x. And I'll write another curve like so, and I'll call it g of x plus 4. And it's a little bit messy the way I've drawn it. It's not always easy. If these are the tangent lines for the respective functions, and the slope, maybe we'll call this, we'll call this x, the slope of g of x and g of x plus 4 are the same. So one reason why these additive constants disappear, geometrically, you can see that by shifting the function up and down along the y-axis, you're not changing the slope, right? And that's why these constant terms disappear. So if we have a function that's x squared plus 4, the derivative is just 2x. And that plus 4 essentially just disappears. And by adding 4, we're just moving the curve up and down. You saw that in the pre-calculus modules we worked through on ALEX. So here are some examples of functions that we worked with in our introduction to calculus. So we've got x cubed, and we want to find its derivative. Well, I'm going to use the power rule, but you might remember from previous videos and from your homework that the derivative of this thing is equal to 3x squared. And if you look here at this next example, 2x squared, well, the derivative of that was 4x. And we might have done f of x plus h minus f of x divided by h, and then taken the limit of this whole thing as h gets close to 0. Now, if we took a whole bunch of similar functions, a whole bunch of similar power functions, right? These are power functions. What do we mean by a power function? We mean that the base x is changing while the exponent is constant. The variable of interest is x, and x is the base, right? It's the base of the exponent. The exponent itself, in this case, we've got a 2 here and a 3 here. That's constant, right? It's a number. It's a constant number. As x is changing, that exponent's always staying the same. It's always going to be equal to 2, or it's always going to be equal to 3, depending on which function we're looking at. Now, you might notice that if we look at these derivatives and their functions, there's a pattern. And that pattern tells us the power rule. So if we've got a power function and we want to take its derivative, there's a power rule that's going to help us. And that power rule is as follows. Suppose I have A and A are constant, right? They're constant. What do we mean when we say, oh, they're constant? We mean, well, they're constant numbers, right? They're just numbers. And if I've got a power function of this form, again, I can tell it's a power function because x, the thing that we want to take the derivative with respect to, is the base to the exponent. I can rewrite this as a times a times x to the power of a minus 1. And this is our power rule. Right? So it's an algorithm that we can use to always get the right answer. We don't have to use those cumbersome limits and Newton quotients anymore. And so, I have the power rule memorized, right? So we had something like, if we've got AXA, then the derivative of this thing is going to be equal to a times the exponent a, and then we're going to have the original exponent minus 1. So if I apply this algorithm here, I've got 1 times the exponent 3 times x to the power of 3 minus 1, and that's just going to be equal to 3x squared. Looking at the next example, I'm going to have 2 times 2, that's the exponent, times x2 minus 1, and I'm going to get 4x. So that's me applying the power rule. We don't have to use those limits anymore. You probably had the answer to these two. If you remember from our last videos and the homework, you would have done these using limits and the Newton quotient. So here's an example. Why don't you try the example yourself? It's a little more challenging, a little more difficult than the ones that I just showed you. You can see that it's a more advanced function, even though it's still a power function. Go ahead and see if you can solve it yourself. Press pause, give yourself a few minutes, and then I will go through the solution with you. Okay, let's apply the rule. So we want to find f prime of x. I rewrite the 1 over 3. It doesn't change, it just stays there. I'll talk about a little bit about that on the next slide. We bring down the exponent, the entirety of it, so it's -9, so we bring down the -9. And then we have x to the power of -9 minus 1. If I do some simplifying, we get -3 x to the power of -10. And we're done. And we found the derivative very, very quickly, much faster than if we used the Newton quotient and took the limit of it. Now, applying this rule teaches you something about multiplicative constants. So I call this rule 2b. And rule 2b says that when taking derivatives, the multiplicative constants are always preserved. So they're always preserved. And that's the capital A in the power rule formula. But this is also true. For the other derivative rules, which we shall learn. So it's always true, not just with the power rule, but with the other rules that we're going to learn in this series of videos. Okay, what do we do if we have a function that looks like this? We've got f of x is equal to 2x plus 4x. I guess that's a little bit boring. Let's do something like this. Let's add a square. So we've got 2x plus 4x squared. Make it a little more interesting and make it so we can't just add the like terms together. Now, how are we going to go about taking the derivative of this thing using a simple rule? And it turns out that if we take the derivative of this, we can treat each term separately. So you'll notice that we could write this as f of x plus g of x, where f of x is equal to 2x and g of x is equal to 4x squared. And if I want to find the derivative of f of x, I can take the derivative of each term separately. So I get 2x, according to the power rule, plus 2 times 4 x minus 1. And maybe, just in case you haven't seen this before, right? If I've got the 2 stays there, it's like there's a 1 there, the 1 comes down, and I've got x to the power of 1 minus 1. If I do some simplifying, I get 2 times 1. What's x to the power of 0? X to the power of 0 is 1. So I get 2 plus 8x, which is just like saying, formally, the derivative of big F is just equal to f prime x plus g prime x. So the derivative of capital F is equal to the derivative of little f plus the derivative of little g. And the next slide summarizes in words, in plain English, the derivative of the sum of two functions is just the sum of their derivatives. And there it is, written, very, very formally. No, I'm not even writing, it's right in the slides. So there's the rule. So you can treat each term separately when you're adding two terms, right? This is a term, and this is a term, right? If we have 2 plus 3, 2 is a term, 3 is a term. Here's an example, classic example from microeconomics. I wouldn't be surprised if you see the exact same function when you're in second year microeconomics. There we've got C as a function of Q, so you can think of that as like a cost function, and a cost function that's a function of quantity produced, the quantity of goods produced, and it's asking you to find the derivative of this thing. Go ahead, press the pause button, give it a try. Use the rules that I taught you and see if you can get the right answer, and I'll give you the right answer in a moment. So there's two rules we want to use. We want to use the power rule. because we have power functions. And 2, we want to use the sum of the derivatives is equal to the derivative of the sums. And so number 2 says that I can treat each of these terms separately, apply the power rule to each of them. So if I want C prime Q, I'm going to get 3Q squared minus 8Q plus 10. And I'm done. And so I hope you were able to get the right answer. If you didn't, there's lots of practice questions in the textbook that you can work on.